So back to the point we discussed about how to model covariate when you have a quantitative variable. So one thing I forgot to mention is that in the literature, people may say, or in other software packages, they say when you have a covariant, in that case, in their usage, it would be some variable of low interest, like age or sometimes even gender. So when they describe it, they say, I covariate out or I regress out that variable. So that description to me is a little bit vague and not accurate in the sense that, whenever we have a quantitative variable or even a categorical variable, when you put it in the model, you can't just say simply I regress out or covariate out. It's more accurate to describe it as basically you control that variable or to fix or to hold that variable at some particular value. That's really what it is about. So that's also is tied with what I was mentioning, the centering issue. So before we talk about, the centering issue, it's one thing I briefly mentioned this morning is that whenever we have outliers, quantitative variable is always have the danger of outliers. Traditionally people may just remove those outliers. That's a little bit harsh and also arbitrary. So a better way is to not simply remove them because that's there's no basis to make such a decision, right? So it's pretty much like a thresholding. So a better way probably is to adopt the approach is called robust regression. So you don't remove them, instead you downgrade them, downweight those outliers. So that is available as an option in 3D MVM. So when you do, but this only works when you have between subject variables like gender or have quantitative variables like age, right, IQ. So, but it does not work. That means it does not work when you have within subject variables, right? So that option will help you to deal with the outliers. There are a couple of other subtleties whenever you have a quantitative variables. Like I'm going to skip this. But it is a little bit tricky. So the reason the centering is important, as I mentioned before, even with a simple case, when you have one group of subjects, just have one quantitative variable. In this case, is IQ. If we only care about the slope, then centering does not matter. You don't have to center because regardless whether you center or not, the slope is always the same regardless, right? However, if you are interested in the intercept, in this case we want to look at the brain response. When we incorporate the IQ as a variable, then centering becomes very crucial because that will have huge impact about the interpretation, of course, about the result as well. So if we don't center the IQ values, we would end up with have the result for the brain response when the IQ is 0 for the population. So of course that's not something we really want. So that's why we need artificially to change the original IQ values. So one possibility is to subtract every subject's IQ value by 100, right? So you artificially change it. Then the new 0 would correspond to the population IQ values of 0. So then the intercept would be interpreted as the brain response when the population, when the group average IQ is 0. So that's one possibility. So that's the population center. Another possibility is the group average. Suppose for this there's a group of subjects at college campus, so the average IQ is a little bit higher than the population. Suppose it's 115. Then now, in that case, we center around this group mean. Then you interpret the result, the intercept, as the brain response at this group average. So you have options. Of course, not just this two. You can, depends on the context. You may center around the other values which you have. Would be convenient for the interpretation. So the point is, you need to keep in mind that centering is a crucial part of this interpretation about the intercept. So this is not again not a theoretical issue; it's more practical issue. So you need to take care of that. Depends on the situation. Sometimes the programs automatically centers each covariant at the group average. But if that's what you want, that's fine. If not, then you have to take some extra step before you put those numbers into the program. We'll come back to that later. So but that's just one group of subjects. If you have two groups, or if you have two conditions, then you have in this case is the age. Then in the literature, in other software packages, usually they just say I covariate out that variable, in this case age. When they do that, then they make a big assumption, means that they don't consider potential interaction between that variable and age. So in the end, they just assume both two conditions, in this case, share the same age effect, no interaction effect. So that's, I mean, if you don't put that interaction effect in the model, of course, the program will give you what you're looking for. That doesn't mean that's necessarily a good model or reasonable model. So ideally, probably you do want to don't make such a strong assumption. The model to help you, to assist you to find out whether such an interaction exists or not. So ideally, you do probably regardless, you probably put the interaction, consider the potential interaction, then let the data and the model decide such an interaction effect or not. So that's the interaction part. Whenever you have another variable in addition to the quantitative covariant. In addition to that, there's also the complication of centering. So in this case, of course, it's a little bit dramatic. Suppose we have two groups of subjects. So they have each group has their own average. Suppose, for example, two groups. One is adolescent. The other group is adults, right? So if age is a covariant. So in that case, of course, adolescents, the kids, suppose the group average is 15.7. That's the average age. The other group is adults. Suppose it's 42.3. So then the issue becomes, what are we going to do with that case, right? I mean, in neuroimaging, often I hear people talk about, and there's a website that specifically say, within group centering does not make sense. But that argument is, to me, it's a little bit troubling because I would say it depends on the context. Sometimes it makes sense to center around the overall mean cross groups. Sometimes you probably have to think about it carefully. Maybe within group centering, it makes more sense. So in this particular case, if with kids versus adults, if we center around the overall mean of the two groups, then we lose the definition of kids, right? Because suppose you combine the two groups, the average age is 27.3, then you do that, the kids, the adolescent group is not kids anymore. I mean, then the group comparison, that would have a big impact on the interpretation, because when you compare the two groups, the age would be something in between, then that's the kids group is not kids anymore, right? So that's the problem part. So you have to be very careful. I mean, sometimes, of course, it does make sense to combine the two groups. That depends on the situation. So that's I mean, depends on where you centered it. You can say the group difference could be dramatic difference. So here, this dashed line in the middle, that means you center around the common mean. So the two group difference is huge, right? So if we move to here, or also move to here, then the difference would be dramatically different. So that's something you have to be mindful about. So that's about the centering. The next topic is about intra-class correlation. How many of you know intra-class correlation? Have you heard of the concept of intra-class correlation? No? So some of you know this. So it's a concept probably in 1970s, close to 1980. So that's this is probably a famous paper to describe the concept. I mean, what this is, it's some special kind of a correlation. But when people apply the concept to FMRI, basically you want to measure the reliability. What kind of reliability? It's when you, for example, you scan the same group of subjects, scanned it twice. Once scanned one time, the next time another, exactly the same task. So you want to see how reliable the effect is. Because it's the same group, same task, just repeated once. So then that's called an intra-class correlation. That's different from the general concept of correlation, Pearson correlation. In that case, those two variables, x and y, can be totally different. For example, correlation between height and weight, right? So those are totally two different physical measurements. Here, we're talking about exactly the same thing. In this case, for example, it's basically brain response. That's percent single change. Both are beta values, percent single change. It measures exactly the same thing, but we just measure the variability. That's why it's called intra-class instead of inter. Inter is the example I used, like height versus weight. That's between two different types of variables. This intra-class, that means the same classification, same thing. So that's, in the literature, people talk about this. I mean, now there are many papers now. I mean, people emphasize the reproducibility or reliability. That's why there's this concept of intra-class correlation can be applied to such a scenario. So there are different ways to describe there are three types. That's why there's ICC1. The first one is the different types. The second one is we can pretty much forget about it. Let's just focus on the first index. So there's ICC1, 2, ICC2 or 1. Sorry, ICC1, 1, ICC2, 1, and ICC3, 1. So I think we can pretty much ignore the first one. The second one, 2, 1. That's pretty much the popular one. I think that's basically you treat both. So the idea is there are two indices here. First one, the I is the subject. The J is, in the case of, suppose we scan the subject twice, that's basically repeat it twice. That's 2 sessions, for example. So you want to say between the 2 sessions, how is the reliability? I mean, it boils down to just the correlation value between the 2 sessions. So that's why if we talk about think the situation as a model, we just have this. You can call it a one-way random effects ANOVA or linear mixed effects model. So that's the concept of intra-class correlation. So that's the ICC2-1. ICC3-1. It's probably this is a typo here. It should be 2-way instead of a 1-way, because both this is subject and this is the session. Both are random effects. So you can think of this model as a ANOVA structure or as a linear mixed effects model. So the third one is we treat the session. I misspoke too, and the I is actually the session. So the session effect as a fixed effects, but the subject, the lambda j is the subject. So in that case, we have a one-way random effects ANOVA or linear mixed effects model. So in this case, we can also calculate the ICC2, intra-class correlation. So the formula is slightly different. Unlike the previous case, at the bottom, the denominator will have 3 variances. But the ICC3, we only have 2 because the session effect is a fixed effect. So I guess that's how much I want to say. There are different ways, and we published a paper last year to describe different ways to calculate it. But so right now, if you are interested in running calculating ICC, right now the 3D RME, that's a linear mixed effects model approach. There is an option, it's called ICC. That option automatically if you invoke that option, it will get the ICC2-1. So in the future, I may probably write another program called 3D ICC, which allows you to calculate all the three types and plus a few other options. So that's the how much I want to say about the intra-class correlation. So the last part, I think, about the group analysis I want to talk about is called inter-subject correlation. That's probably some of you have heard of naturalistic scanning, right? Anybody doing naturalistic scanning? No? That's, I mean, the typical FMRI, you have a task, right? You have to ask the subject to do something in the scanner. That's one scenario. Another scenario is the other extreme. The subject would do nothing. That's called a resting state, right? So about 10 years ago, people start to think about something in between. That's because the tasks the subject perform in the scanner is too artificial, like you push a button or you view some emotion images, right? It's not, those are a little bit like or building or face. It's a little bit remote from what we experience in real life. So it's too artificial. So people argue maybe we should try something closer to real life experience. So that in that case, the typical thing people do is watch a movie, because that's the subject in the scanner watch a movie. That's I mean, it's some events, right? So it's close to real life. That's one possibility. And people have also done like music listening in the scanner, or political speech, or compare political or some speech in different languages. So people have done things like that. So that's called naturalistic scanning. So I mean, one extreme case in Germany, people have, collected data with the subjects watching Forrest Gump. That's almost 3 hours. That's a lot of data. They put the data online, actually available. So I don't believe it's a whole brain, because for some reason they just part of the brain. It's a probably high resolution data. But anyway, so I'm going to briefly talk about a little bit about this, since nobody seems. Okay, but you may do something different. But let's say what we can offer here. So that's I'm to be. But this is just an overview. So it's usually it's a movie watching and music listening or speech or play games sometimes. So the classic paper is this one, has in 2004. So that's a little bit over 10 years ago. So that he started this, this concept of inter-subject correlation. So from modeling perspective, some people do it. Use the semantics. They annotate the movie, for example, or then try to do it sort of like similar to task related. But here, this is more general. It's also simpler case that you just have a time series. People wanted to. That's why it's called the inter-subject correlation. So because the subjects are pretty much synchronized. They're doing exactly the same thing, but regardless the content. So they just calculate the correlation between any pair of subjects. So suppose you have 5 subjects. So you A, B, C, D, E. Then you just calculate between subject A and B, subject A and C, subject A and D and E, so on and so on, so on and so forth. So 5 subjects, you end up, then you have what, 10 combinations, right? So that's 10 possibilities. So they calculate the correlation. That's why it's called the inter-subject correlation. So 5 subjects, you end up with 10 pairs. Then what are you going to do at the group level? So that's the question. That's the challenge as well. So that's what I'm going to talk about. So here I list the complexity of this case. So 3 subjects, you end up with 3 pairs, right? So 4 subjects with 6, 5, 10, then you keep going, that number, I mean, goes up pretty quickly. So n subjects, you end up with n times n minus 1 divided by 2 inter-subject correlations. Well, the challenge is that the group level. What are you going to do? The problem is n subject, you end up with n times n minus 1 divided by 2. I mean, what are you going to do t-test? But the problem is those n times n minus 1 divided by 2, those pairs are not independent of each other. Some of them are, some of them are not. So what are you going to do? That's the challenge. So why is a challenge? So if you look at just the one group of subjects on that matrix, so with n subject, so the S1, S2, all the way to Sn, that's the subject, right? Subject labels. So the n times n minus 1 is basically it's the half of the matrix excluding the diagonals. So you can either focus on the lower part or the upper part. Suppose because it's symmetric, right? Correlation matrix. Suppose we focus on the lower part, the lower triangular part. That's exactly n times n minus 1 divided by 2. So there are correlation values, Pearson correlation, because we calculate the correlation between the same voxel in my brain and the same voxel in your brain. I mean, then you have the Pearson correlation. So when we usually do analysis, we need the Pearson correlation value is bounded by between minus 1 to 1. The way we handle that, we Fisher transform it to z-score. Right? That's just for the convenience to make assumption Gaussian distribution. So on the right-hand side, that's why we have that Z matrix. But so again, we need to focus on the lower part. So what are we going to do? That's one group. Over two groups, we would end up have this structure, the color structure. So even though it's one matrix, but if we combine the two groups, we end up partitioning those two triangles here. This is the first group. This is the second group. We can compare the two groups, or this could be the intergroup. I mean, between group. It's kind of cross-group interaction or similarity. So you can do either compare those two groups directly, or you can compare the group versus the cross-group similarity. So the different things we can talk about. So what's the challenge? Exactly what's the challenge? Suppose we have, in this case, we have 5 subjects. With 5 subjects, we have 10 pairs, right? So n times n minus 1 divided by 2, that's 10. So we put those 10 numbers, there's these scores, 10 numbers here and 10 numbers here. So you can see this is the correlation structure for those 10 Z scores. Why do we have that structure? Well, diagonals ones, right? Nothing special about that. The zeros, why do, for example, here this we assume it's not 0. Why is that 91 is not 0? Look at the x and the y direction. On the horizontally, that's because we have this. Horizontally that's Z4, 1. That means that's the Z score between subject 4 and subject 1. Vertically, that's between subject, Z5, 1. That means that's the Z score for subject 5 and 1. Those two Z scores share a same subject, subject 1. So because that share that subject, it's reasonable to assume those two Z scores are correlated. So if you look, same thing for this one, because this two Z scores share the same subject 4, right? And some of the zeros, because those two Z scores, they don't share any same subject. That's why they are zeros. So that's why this is difficult to handle for, when you go to the group level because of this structure. What kind of a structure is this? Some of them are non-zeros, some of them are zeros. Can you see some pattern of this? Well, maybe there is a pattern. That pattern is just so hard to capture it. So as far as I know, there's no way to easy to capture That is structure. So what have people done so far? I mean, historically, I mean, in the early days, people have simply just do T. I mean, even though there's a correlation structure there, they just assume, I mean, it's either they adjust the degrees of freedom, or they say to one simulation is sort of like a t-test. So that's one approach. Then recently, there's a MATLAB toolbox called the ISC toolbox, the inter-subject correlation toolbox. That one is very popular. That one, how do they do that to handle this? They deal not at the group level. Instead, they randomize the time series. So of course, first they calculate the real correlation matrix of voxel. So that's the real z-scores. Then they use the concept similar to the permutation test, for example. They randomize the time series. So they randomly shuffle those, changing the order of the temporal sequence of each voxel's data. So randomize this, then calculate that matrix. So they're doing that many times, for example, 5,000 times. So then they use that as a null hypothesis, null distribution. So then compare the real z-score versus that null distribution, right? So then they come up with the p-value. That sounds reasonable, right? You sort of you randomize, you randomly shuffle the data, they use that distribution. That's pretty much like nowadays to group level analysis. For example, FSL, they have randomized, right? So that's you shuffle. It depends on the situation, but they shuffle at the group level. This case, they shuffle the time series at the individual sublevel. Then they use that as a null distribution. I mean, that sounds reasonable an opinion, but how would that will behave? Nobody before has done any to check whether that does control the false positive rate at the nominal level. Nobody has done that. So that's the one available solution. Another solution called leave one out. That's a little bit earlier version, actually. It's by the same group. The idea is that suppose you have 10 subjects, you calculate the inter-subject correlation. With 10 subjects, you have 45. So they do that. What do they mean by leave one out? So each time they take one subject out, then calculate the average time series of the other 9 subjects, then calculate the correlation between that one subject and the average of the rest. So they do that for each subject, right? So you have 10 subjects. First, they take the first subject out, the other 9, then you calculate the correlation value. So do the same thing for the next subject. So in the end, 10 subjects end up with 10 inter-subject correlation, but that inter-subject correlation is one subject versus the rest of the group. So that's the called leave one out. In the end, you end up with 10. It's not inter-subject anymore, but it's 10 some correlation values. Then they go to group level, they just do the typical t-test. So that's the alternative approach called leave one out. But in reality, all those methods are actually, in reality, they don't perform well. And we published 2 papers about this. The first paper we demonstrate previous methods would not work well. So the first paper, we also adopt a nonparametric approach, but I'm not talking about the details because it works well, but it's the nonparametric approach is limited in terms of its computational cost a little bit high, and also it's not flexible in terms of modeling, right? If you want to have covariant, or you have to do something else, then it's just not flexible enough. So that's our first paper basically focused on either do bootstrapping or do a permutation test. But instead of doing that at the individual subject level, shuffling the time series, instead we shuffle among the subject. We calculate the correlation matrix first. That's it. Then just shuffle at the subject level. As long as we do that, then we did a subject permutation or bootstrapping, depends on the specific scenario. We we performed the simulations, showed the false positive rate controllability is pretty good, unlike the traditional approach. So that's the non-parametric approach. So the second paper we published in 2016. This we switched to parametric approach. The parametric approach is nice. I mean, you can accurately characterize the data competition. So for example, on the left-hand side, it's the inter-subject correlation between subject I and subject J. That's a z-score, right? So that on the right-hand side, we do this. First, we have the intercept, which is the basically group average correlation. I mean, it's a z-score, of course. And that's the population average. Then we have two extra terms. Those two extra terms, basically it shows the contributions from the two subjects, subject I and subject J. Then we have the last term is the residuals. So once you realize you do this decomposition, then suddenly this is just a linear mixed effects model. I mean, so we have the fixed effects with the intercept plus two random effects. Those two random effects are the contributions from those two subjects. I mean, once you realize it, that's pretty intuitive, right? So once we have this model, then we make a reasonable assumption. The two random effects, I mean, we just assume the Gaussian distribution with the same, of course, from the same population with some variance. Then we have this model, then pretty nice. Then also some nice property as well. Remember I showed you the correlation matrix. Some of them are correlated, some of them are not. We can exactly capture that correlation, and we show the bound that between 0 to 0.5. You cannot go beyond 0.5 actually. So that's a nice property, and the mathematical proof to show that why there's a bound 5. So I mean this exactly, I mean you can calculate here why it's 0.5, because only when this switch is, I mean small lower bound 0, then you get 0.5. So it's very nice. So with that model, basically it's very convenient. So either you have one group or two groups, or even when you have covariant, then this basically the linear mixed phase model is more adaptive, and we also did the simulations to show the false positive rate control is also pretty good. So that's the inter-subject correlation part. I mean, in case anybody interested in this, we probably planning to, I mean, I promised this a while ago, I mean, to have a program to do this kind of a group analysis. So here's a basic example. We have two groups. This is the exactly same data we used in the second paper. So we have totally 48 subjects, 24 males and 24 females. The subjects watched in the scanner watched the movie, actually 6 movie clips. Totally there are 400, a little bit over 400 data points connected. So on the first image that shows the nonparametric approach. It's either bootstrapping or permutation test. Then the second one is the linear mixed effects modeling. I just showed you that. So the two results basically pretty much similar, but the parametric approach is nice. They also give you extra information. So I can also calculate the wall, the third image. That's shows how correlated among those pairs. Remember, the wall is the correlation in that big matrix. So that's the third one. In addition to that, I can also show the variance and the residual variance and the subject cross-subject variability. That's the fourth image. So it's pretty nice, and that's why it's the parametric approach is usually better than non-parametric. Even not just for inter-subject correlation, even for typical group analysis. Even though they claim non-parametric approach is little bit, I mean, in terms of a controlled false positive rate is great, but in terms of modeling, it's way much less flexible and less adaptive. So I think that's pretty much I want to talk about the inter-subject correlation. So people are probably using this for, can be extended to other modalities like EEG or MEEG, but it's not as popular as in FMRI. Any questions about the intra-class correlation or inter-subject correlation? To talk about, now switch a little bit different. I mentioned at the beginning of group analysis that the typical FMRI data analysis at the group level, we do whole brain, right? That approach, there's something need to be challenging. Well, for this part, there's I'm talking about the motivations, why I want to do RI-based group analysis instead of a whole brain. I mean, ideally, theoretically, could apply the approach to the whole brain, but that's little bit, right now, it's not feasible, but we'll see why. But to focus on, keep focus, that let's just talk about the RI-based. So that means we have a bunch of RIs. So my motivation is, the little bit background is that, I mean, about the cluster stuff, right? There's a controversy about the false positive rate controllability is a little bit not as strict as desired. So there's a famous paper about in the news, right? So that's one, that's the background and motivated me to start to think about this approach, because that penalty usually is very high, very severe. The cluster stuff, it's people sometimes you really have trouble have your clusters to pass that threshold. So that's one major motivation. Of course, there are a couple of other scenarios like people so-called graph theory, right? So we have, for example, within state data, you calculate the correlation matrix among some number of RIs, like 200 RIs. You have the correlation matrix from each subject. How do you handle group analysis? So that's another motivation for me. And you can, same idea in the DTI, you have a white matter connection, you have a matrix, a big matrix too, right? So you have gray matter regions, then you look at the white matter, the bundles, then see if they are connected. You have you have that matrix as well. Then at group level, how to handle that? That's another challenge. Of course, we can also think about the inter-subject correlation I was talking about at the RI level, but that's something later. So those are the background issues in my mind when I was thinking about how to handle this. How can we do better than the whole brain analysis at the voxel level? So that's basically the layout of this small session about the RI-based analysis. So the motivation is that paper 2016, the Eklund paper, right? So that's I mean, the criticized different software package has trouble to keep the false positive rate at the nominal level. So that's so my viewpoint is ideal. I mean, if you really trust that approach, yes, that argument does hold well. I mean, it's the criticism is valid. However, we look at it differently, then we may have a different perspective. I will say that a little bit later on. So before we talk about that, let's start with why do we care about the false positive rate or family-wise error or type 1 error, whatever. So the problem is when with the traditional statistic, we always started with the so-called null hypothesis, right? So for example, in the brain, it started with, in this region, nothing going on, no activation. That's the null hypothesis. Whenever you do statistic, you have that null hypothesis. So that's your starting point. So you pretend nothing going on, then you basically you put up a straw man, then you start to attack that. So how do you attack? You calculate, for example, typical way you have this t statistic. Okay, now I have a t statistic. The t statistic is large, 3.7. Okay, now the p-value is small, 0.001. now we have doubt about the original null hypothesis. We can say the original null hypothesis is not reasonable. We can reject null hypothesis. We take the alternative hypothesis, which is now we can see the description is at this region, it's statistically significant. That there's people usually don't mention that word statistically significant. That is statistic. That either verb people usually forget to attach to describe the significance. Well, that usually when I read a paper, I always attach to that. The reason is that simply because the p-value, it's not about the effect itself, whether that effect is significant or not. It's not. The effect itself can be big or can be small. So when they say significant, they only mean that's because of the statistical value itself. It has nothing to do with the effect. The effect can be big, can be moderate, can be small. So that's why implicitly they simply means the statistical significance. It's not about the effect significance. But more problematic is that in the end, people make a decision. That decision is binary, is dichotomous. Either you have that, you can make the claim, or then if it is fail, if that t-value is small, it fails to survive the thresholding, then what? Does it mean does that have, that region was not activated? Or no? Well, people have to make such a decision, dichotomy decision. People's mind, they simply treat that scenario as there's low activation. But in reality, that region can be activated. There's simply several reasons it fails to reach the significance. Can be the effect itself is too small. We need a bigger sample size. That's one possibility, right? So the other possibility is, in brain, there can be other scenarios. Alignment is not perfect, or data is just too noisy, right? So that's the background. So how can we avoid that dichotomous decision? And also, we need to challenge the approach, that is threshold approach, the p-value, and also the strategy of assuming that there's nothing pretending nothing going on in the brain, then we do something. So that's something we need to talk about. So there's, instead of to have that straw man, that a witch hunting, so maybe we can do something different, because the traditional approach is always you start that so-called conditional probability, right? You pretend nothing going on. That's null hypothesis. So that's something. It's called a lot of illusion or misunderstanding or misleading statements. Is that because people's mind maybe they think is the p-value is when we have my data, then that's the likelihood you would get nothing going on in the brain. No, it's not. The real p-value is you pretend nothing going on. What's the chance you would get the current data? So those two things mathematically is not the same, but people usually misinterpret the so-called p-value. So whenever you say the p-value, 0.05 or whatever the p-value you have, it's a conditional probability, and that probability is pretend nothing going on. What's the chance you would get the current data? That's the p-value, the meaning of the p-value. So there are many things. People have been criticizing this. It's called NHST, null hypothesis significance testing. So or this dichotomous decision. So let's even put those criticisms aside. From practical perspective, is that applied to the typical FMRI analysis. In the end, when you make a decision about a cluster, the current approach is how do we control the false positive? If it's just one voxel, life is easy, but for the whole brain, usually we have, for example, 200,000 voxels. The approach is the so-called cluster, right, to cluster stuff. Based on the spatial extent, how big the cluster is or how small. This is so-called multiple testing problem. Some people call it multiple comparison. More accurately, it's more about multiple testing is the multiple comparisons. The subtle difference is that because for FMRI, we're using the same model, which is the testing is exactly the same. So it's 200,000 voxels, we repeat the same model. The real multiple comparison is more like we need to do ANOVA, for example, 3 conditions, A versus B, B versus C, A versus C. That is a multiple comparison issue. So for brain imaging, actually, well, that is an issue for brain imaging, but that's a minor issue if you really have multiple conditions. But we are talking about here is not the real multiple comparison. It's called multiple testing because the same model is repeated many times, as many as the number of voxels. So that's why more accurately it's called multiple testing problem. So, I mean, the approach is immediately the term bump-only correlation would jump into your mind. But nobody does that. That's because the penalty is just too severe. Nobody wants that to apply that approach. So to avoid that severe penalty, people do so-called cluster stuff, right? So cluster stuff, there are a few approaches. First of all, there's SPM's random field theory. That's pretty much using a similar concept in FNE is using Monte Carlo simulations. So in that sense, you choose a so-called primary threshold. For example, threshold of p.001, whatever the t value is, but threshold based on p.001. So once you threshold that, you find some clusters, right? A bunch of clusters. That's clusters can be, some of them big, some of them small. Then you decide which cluster can pass some threshold in terms of the cluster size. How do we decide that cluster threshold? That's in FNE, for example, you want Monte Carlo simulations with noise, not with your data, with the noise. You control the so-called false positive. That means, well, really nothing going on, so that's why we use noise. Then use the same brain structure, the spatially correlate the data with noise. Then randomly generate to shuffle them, then say, okay, 180, for example, 5,000 times, then count the clusters with different sizes. Then control how many of them passed, for example, control the 5%. That's why how you come up with the cluster threshold, the minimum cluster size. That's the FNE approach. That's implemented in a program called 3D. Same. That's also, the option in 3D t++. That's exactly the same thing. In SPM, there's a random field theory. It's a different concept, but the idea is pretty much the same. It's just in the end, you based on the spatial structure, then find out there are some minimum cluster size. So in the end, you come up with the survived clusters. So that's the one approach. A second approach, the first approach is a little bit troubling, is that you have to start with a primary threshold, 0.01, for example, sometimes 0.05, 0.005, for example, or 0.02. But that choice is arbitrary. So I will talk about later on why that is arbitrary. But I think we should take a break, then come back, continue the rest of this part.